So we're talking about question 3, the decomposition. Decomposition of hydrogen peroxide was studied, and the following data were obtained at a particular temperature. Decomposition of hydrogen peroxide. So you have the rate. For question 2, there is one part that we have left. The one telling us when time is equal to 2.7 and 10 to the power per second, find the concentration of this. So if you know the order of the reaction, if you know the order, which means we even know the integrated rate law, so just have to substitute in the values. You get the initial concentration at this time, then you can find the concentration at this particular time. Hello? I told you to tell me once we are done, because right now I'm doing an online tutorial. I can't wait, because I'll be done shortly. Eh? Okay, then tomorrow. Okay, I need to print out the. I'm using the phone to check out for the questions. The decomposition, so this we have the rate expression of change in T. The decomposition of hydrogen peroxide was studied, and the following data was obtained at a particular temperature. So you have got that table, starting from when the time is 1 to the time in second, that is 3,600. Determine the rate law, the integrated rate law, and the value of the rate constant. And also calculate the concentration of peroxide when the time is 4,000 after the start of the reaction. After the start of the reaction, determine the rate law. The rate law determine the electron, because we're talking about the decomposition of hydrogen peroxide. So the only reactant that we have, I know that in the electron, you only include the reactant, not the product. Why?
Yeah, we are concentrated on the results. Because we are concentrated on the results.
So this, our electron in this case is your P, H2O is N. Because the N we don't know, because N does not depend, is not equal to the coefficient. So you need to determine the value of N. So that would be our electro, the integrated electro. The integrated retro as well as the value of the rate constant. So even this one, just like we did for the second equation, because just to look at the value, we cannot tell that the integrated retro we are going to write for peroxide is first order, zero order, first order, or second order. We cannot just tell by just looking at the values. So it's the same. You have to plot. You have to plot the one that is going to give you a linear slope. Then you know that is what the integrated retro that you are going to use for the decomposition of peroxide. So it's the same value that has been given. Just make the table, the time in seconds, you have the concentration, and you have this, the natural log of the peroxide, and we have 1 over the concentration of this. The concentration that we have 1, 0.91, 0.78, 0.5, 59, 0.37. 300. Then we have 600, 1,001. And this goes on. It's the natural log of this value of the concentration that we have here. The natural log of 1 is what? Try to give you a 0. Yeah. So 1 over 1 to give you just 1. So you fill in what the table, then you plot this. You plot, you know the plot for the natural log versus time, that is first order. The concentration versus time, that is 0 order. 1 over the concentration versus time, that is second order. If any of these will give you a linear slope, then you know that is what? That will tell you the order of the reaction, and also the integrated retro you are going to use for the decomposition of hydrogen peroxide. Yes.
When plotting, are we supposed to plot them separately, like concentration for that one, then
you plot them separately? Because you know that Because you know that for first order we have this. We have to then with this we have the time seconds. Because this is for the first order. First order. For the second order, on the y-axis, we have 1 over the concentration of the peroxide. This is for the second order. For zero order, we just have the concentration here. This is time. For first order, it will give you what? If you get a linear slope, then you know that the reaction is second order. For zero order, it also give you a linear slope, then you know that the reaction is for zero order. And for second order, this one has to give you a positive linear slope. They know that it's second order. The same, the value of the rate constant. The rate constant for second order. For second order, the slope is equal to the positive k. For first and the zero order, the slope is equal to minus k. Question 4. That's okay. Question 4 has been told that for 40 degrees, the hydrogen peroxide would decompose according to the following reaction. Yeah. So she's giving us composed to that. The following data were collected for the concentration of hydrogen peroxide at various time. And we have the different time and the concentration of the peroxide. For zero, we have 1.0, which is molar, 2.16 and 10 to the power 4. This is 0.5. And 4.32 and 10 to the power 4, 0.25. More. So you have been given this data, and for part A, they are asking calculate the average rate of decomposition of hydrogen peroxide. Calculate the average rate of decomposition of hydrogen peroxide between this time to 2.16 and 10 to the power 4 second. Again, using this rate to calculate the average rate of production of oxygen gas over the same period of time. Calculate the average rate of decomposition of hydrogen peroxide during that time, and use this rate to calculate the average rate of production of hydrogen gas. The part B, what are these rates for the time period of okay. So for this one, calculate the average rate for the decomposition of hydrogen peroxide. The time that we have from 0 to this. Anyone? Okay. Yes, sir. Just be on the phone. You know that the rate of decomposition of the peroxide, say R is equals to say 1 over 2. We have this change in T, not so. And with this, I would say minus 1 over 2. The concentration, change in concentration that we have is 0.5. 0.5 minus 1.0 over the change in time that we have is 2.16 10 to the power 4 minus 0, which is seconds. So this, if you do the calculation, what value are you getting? Because this will give you negative 0.5.
This is negative 1. It's 1.157 instead of 1.
Negative 1.157 times 10 to the power negative 4. Now why negative way? Because this gives you negative and you have a negative, so the negative goes.
It's positive.
Yeah, it's supposed to be positive. So then that will be the rate of decomposition of the.
So why are you getting those values like 1 over 2?
1 over 2. The coefficient. The coefficient.
Is 1 the coefficient for oxygen?
Yeah, so yeah, for oxygen, then the oxygen coefficient is 1. Because they're getting from the general equation. If you have equation A, say B, give us C. So the rate of reaction for this, we'll say that R is equals to, we have for the reactant minus 1 over A, this coefficient, the change in concentration of A over the change in time. For this, we have 1 over C, the change in C over the change in time. So in this case, for the decomposition of this coefficient, that's where this 2 is coming from.
So it should be one should be always on top when you make the reference.
Yes, yes,
Sir,
yes.
but why is it 1/2 instead of 2? Why are we putting 1/2?
Mm. Why 1/2 instead of just 2? Mm.
Yeah, yes, sir.
Mm. Anyone? It's a question to everyone. Mm. Why is it 1/2 instead of just 2? You multiply by 2. Mm. Mm. Yeah, what your friend is saying, it's called it the coefficient. Are you seeing the general expression for the rate of reaction?
Yes, sir, I can see it.
Yes. And so the coefficient we are dividing towards to the concentration, to the change in concentration that we have.
Oh, okay, okay.
Yes.
I get it now. Thank you.
That's also have a question. When there's no 2 there on the front of the hydrogen.
So like I'm sure like if you look at this one, if you were to write the rate for oxygen gas, you know that this is 1/1. So 1/1, the same one just to write what? Not write anything. Then to write the change in the concentration for oxygen over the change in time.
Sir,
Yes.
I got. Well, why did you write the message there on the rate?
Yeah. Saying that the change in concentration for the reactant is decreasing. The concentration is decreasing. So the change in concentration will be negative. But you want the rate of reaction to be positive. So that's why we have included what? A negative. A negative just to make the value of R positive. Yes. So the other part. The units here will be more per second. Molar per second. Calculate the average rate of decomposition between that time using this rate to calculate the average rate of production of oxygen. Use the same rate to calculate the average rate of production of oxygen over the same period of time. Now it's timing the average rate of production of oxygen over the same period of time from 0 to 2.1 times 10 to the power 4. So if we were to for this, we know that the change in O2 over change is equals to minus 1/2 and this H4 over this also.
Sir,
Yes.
now how about if we, because here we are already given the rate, then we have found there. What if you just use the same formula?
Which one?
That is a question.
Yeah, because we have been told to say that we are studying the rate of decomposition of this. Now they're asking us to find the rate of formation of the oxygen. So if we are to use what the coefficient, just like this is the question 1. Question 1. So in this case, the rate of formation of the oxygen. So in this case, just have to be this one that we have here, which is 1.157 and 10 to the power -4. Okay, the second. This cause the coefficient in a case where we have like for
My point is just lines.
yes.
Yeah. I was saying, what if we just do the same thing? Because this thing is just one and the same. Where we have put that one, the 1/2, we have already found it here.
Yes, we already found it.
We just equate to, we just put it to that.
Yeah, we just equate to this. Since the coefficient G is 1,
Yes.
the coefficient E is 1, so which means this is just equal to this value.
But now, on the times, not going to change.
We have been taught on the same time, this from 0 to 2 times 10 to 2.1 times 10 to the power 4 seconds.
Yes. Are we not supposed to substitute it on the what? Yes. Hydrogen and oxygen combined the times there.
We know that the rate of this is equal to this. So how we determine the rate? The rate is the change in concentration one. The rate of reaction, the change in concentration over time. So this value that you have found, there is change in concentration and time. So there's no need to find in the time. Yes.
But why are you doing this? Because why are you doing this?
You want this to be like what?
Because, sir, if it was like the way you're saying, you would have written like that, the way you've written. Right? Yeah. Because there, it must be substituted.
So you're saying that this rate, this is the rate of formation of oxygen. The rate of formation of oxygen is equal to this. The rate of decomposition of hydrogen peroxide. The rate of decomposition of hydrogen peroxide is this. This is the rate of decomposition of hydrogen peroxide. And the rate of decomposition of hydrogen peroxide is this what we found here. So if the rate of formation of oxygen is equal to the rate of decomposition, which is this value, then the rate of formation of this is equal to the same value.
Now, excuse me, sir, a question.
Yes.
On the rate of production for oxygen there, why didn't you put a negative sign there? Because on the rate of decomposition for peroxide, you put the negative sign on 1/2.
This rate, the rate of decomposition for hydrogen peroxide. Hydrogen peroxide. Remember this rate of this value, the other value, this value.
Yes.
The negative V, the negative will cancel the negative change, the negative value that you get from the change in concentration.
Okay.
Yes. So this negative is telling us, so it will cancel with the negative value that you get from the concentration to give us a positive value.
Okay.
Yes. This is just the formula for the decomposition of the hydrogen peroxide. But if you have done the calculation, the value that you're going to give, it's going to give you a positive value for the rate of reaction, the rate of decomposition.
Sir,
Mhm.
I'm still not confused. Sir, those things are a combination of hydrogen and oxygen. Now, how can they be equal? The hydrogen peroxide and the oxygen.
We are talking about the rate, the rate of decomposition and the rate of, remember, this hydrogen is coming from this one, hydrogen peroxide. This one decomposes. As it composes, giving out H2O as well as oxygen. So this decomposing, this is forming. Yes. So now they are asking you to find the rate at which this is being produced. So for you to know, for you to get this, so to determine this, we have used the known rate.
So like to answer the question, how do we answer the question? Just can you just write the direct because
we know the relation to say that the rate of formation of the production of oxygen is equals to the decomposition of hydrogen peroxide. The rate of decomposition of hydrogen peroxide is this.
So I have to state, and the statement begins the statement.
No, this is a statement. This is a statement. Don't have to be putting in word writing sentence, because this is the whole sentence. What I'm saying that the formation, the production of oxygen is equals to the rate of decomposition of hydrogen peroxide. The rate of decomposition of hydrogen peroxide is this. The rate of formation of oxygen is this. So instead of writing the sentence, it's better just to write this. And for this, we have calculated already. We just have to equate.
So does it also apply to that other molecule water?
With this, if we are to write the rate of rate of reaction, we are not going to include water. Why? Water, liquid and solid, the concentration remain constant. The initial and at the final, the concentration remain constant. So you find that the concentration will give you 0. So rate of reaction will give you 0. So that's why we are not included in the rate of reaction. For solid and liquid, they are not included in the rate. Look at the other question. It's just the same. Determine the rate rule, the integrated rate rule, calculate the.
Question 4.
That is
Part B of question 4. What are these rates for the time period? That's for the time period reached to 2.16 and 10 to the power 4, and the time that we have 4.32 and 10 to the power 4. This we have the concentration of 0.5 and 0.25. So what are the rates for the time period of that? So unable to get the determine the rate for this time period. I'm just the time, the change in time, and the change in concentration. So can that mean the rate? Eh? Yes. Time was moved. So we'll continue from here tomorrow. Because for these guys who are online, you have less than 10 minutes before this Zoom meeting end the 40 minutes that they give for every session. And for me, because not suggest such what if you were to look at question 5 and question 6. Question 5, just from that equation that you have been given, then determine the rate flow, calculate the value of the rate constant for each experiment and the average value for the rate constant.
Depending this one, the view, may also include the power of
Yes. For the peroxide, which is what that use the peroxide here. Over the change in concentration over the change in time. We're going to determine the rate over that period. Question 6, just question 6, which has got the different parts, which are even included the half-life of the reaction. But we'll see what we can do tomorrow. Tomorrow, I'm sure tomorrow won't have a reaction. Supposed to meet tomorrow at 12 to 13.